Hello everybody and welcome to the last part of my collision detection tutorial series. In today's video I'm going to be going over the implementation for the Fauerby method, which I went over in the first part of this video. This is a fairly long method, there's some complicated things in here, so I'm going to stop with the preamble pretty soon and just get on with actually writing the code. If you're confused at any point, it's worth skipping back to the last video or giving a read to the paper that I'll leave in the description. So we'll start in an empty class here that I've called my Fauerby detector. This takes in our usual does collide method, so this is going to be how the collision detector interacts with it. This takes in two entities and a velocity, so importantly this is the only one so far that matters the order that the entities go in. We'll want to put in our moving entity along with its velocity, followed by the entity to check against. So I've just made a quick method here, which is my in-range method. Literally all this does is it checks if a value is between another two values. We use this a couple of times, so it's worth having it around. I'm making the first method here, which is calculating a spheroid. This takes in a bounding box, and it is the same bounding box from my bounding box tutorial. So if you're unsure how to construct one of them, it's worth checking out the tutorial. All we're doing to make the spheroid is we're taking 1 over half of the width, half of the height and half of the depth. So we take the maximum value on the x minus the minimum value on the x, etc. It has occurred to me that instead of doing 1 over the value over 2, I should have really done 2 over the value, but this illustrates the point a little bit better. Next we want to make our calculate position method. So this calculates our player's position in regards to the sphere, and ideally we want that to be in the center of the sphere rather than the actual origin the model is at, which often doesn't extend below the ground, for example. So to do this we just take the minimum value on each axis plus half the width, half the height and half the depth, and that puts the sphere right in the middle of the bounding box. Now that we've got these two down, we can start work in our does collide method. So we create the bounding box for our primary entity, and I just do that using my bounding box detector. I left that method public for this reason. We then take the spheroid space for the bounding box and the position. I did say in the video that spheroid space would be a matrix, not a vector. So if that's confusing you, then a matrix with values only along the diagonal, which we use exclusively for transformation, we might as well just consider to be a vector and perform vector multiplication on everything that we're passing through it. So that's exactly what I'm doing here. In fact, I'm taking my primary position and I'm putting it into the spheroid space, and to do this you just multiply the x, y and z by the x, y and z. We also need to do the same for the velocity, so I'm going in and multiplying the velocity by the spheroid space x, y and z as well. There's a fair amount of vector multiplication in this method, so I would advise, if you can, setting up a multiplication through vectors for other vectors and scalars. LWJGL doesn't have this natively, so I'm just adding it in to illustrate a point. We're now on to our next method, which is putting the vertices of the second shape into the world space and then into the spheroid world space. So to do this we do what we've done before, which is just take all the vertices and put them into world space by multiplying them through the transformation matrix for the entity. But crucially for this method we're also going to be multiplying each vertex through the vector 3 that we call the spheroid space. So same as ever before, we just extract the vertices, create a transformation matrix and iterate through all of the vertices. We're going to multiply each vertex through the transformation matrix we've created, and this just gives us a vector 3f in world space. And once we've done that, all we're going to do is we're going to take that world position vector that we have and translate it through the spheroid space that we previously calculated. This is very simple, but it does need to be done for every vertex, and this means we now have the player's position in spheroid space, their velocity in spheroid space, and every vertex of the second shape constructed in spheroid space. So now we've got that, I'm going to hop back up to the top and we can use this to create the second shape in a world position and in spheroid space. Now that's called, we also need to extract the indices, so this is just how we're going to work through the shape. And they don't need to be transformed, of course, because they are just references. Now onto the actual calculations. We're going to want to set up a plane class to test our intersections with the spheroid and the plane. Now a plane can be defined in one of three ways. You can use an equation, that's ax plus by plus cz plus an offset, by a point on the plane and the normal of the plane, or by 3 points on the plane. Our first constructor takes in a point on the plane and its normal. You can extract the normal and the point very simply, and the equation is just the normal x, the normal y, the normal z, and to calculate the offset we just take the negative value of the normal values by the origin values. And now our second constructor, this one takes in 3 points, so you can define a plane by 3 points on the plane. Now we extract the normal from these 3 points by taking the cross product of two of the points subtracted from a third, and we can set the origin, or a arbitrary point on the plane, to be any of the 3 points we were given. Then we just take the equation, part 1, 2 and 3, from the normal as usual, and the offset is exactly the same. So now we can construct a plane in one of two ways. This is going to make it easier for us to do our checks to see if our spheroid intersects the plane at any point. So there's just a few more methods we want to create within the plane class. The first one is our on-same-side method. What this will do is, given a plane in the world, it will check if an arbitrary point is on the same side as another arbitrary point. We do this by placing the 2 points on the plane space, so we just do this by multiplying each one through the equation, and if they are on the positive side of the plane then the result will be positive. If they're on the negative side of the plane it will be negative, and we don't especially care if it's positive or negative, we just care if the two have the same sign. So to extract that we just multiply them together. If the value is above 0 they had the same sign, if it's not then they didn't. We're going to make our sign distance to method here. This will tell us the sign distance from an arbitrary point in space to the plane. To do this we just take the dot product between the normal and the point we're given, and we add in the offset from the equation. And finally here we have our in triangle method. This is going to use another method which I haven't put in yet. This is the same side method. But this is our last useful class. It will just check if a given point, which we've called point, lies within a triangle defined by 3 points, point A, point B and point C. And to do that we do use our same side method here. The same side method takes in 2 points, so that's point and point prime, and 2 points that construct an arbitrary infinite line. And what we do here is we check to see if the 2 points are on the same side of a plane constructed through that arbitrary line. And that just uses our method from earlier to check if 2 points are on the same side of a plane. Now that we've got this, we have everything that we need for our plane class. So we can go up to the top and we can start working with this to check for detections on the sphere. Now it's at this point that I realise I've made a few mistakes in the methods above. So you're going to get a cut to me in future putting in the code, which means you probably won't see it for the rest of the video, but this is the correct code, so this is the one you'll want to copy. What we're doing here is we're iterating through all of the indices, obviously 3 steps at a time. We take t0 to be our starting position, so that's our position at the time 0, and t1 to be our ending position, so it's position at time 1. We want to take the 3 points, so this is just our indices, so this is just our secondary shape taken from the point of the indices. And we construct a plane from these 3 points just by calling the construct plane method and using the 3 points. We then want to check if our dot product between the normal and our velocity vector is 0. If it is, then it means that the plane lies orthogonally to our velocity vector, and it can either never collide or it's constantly colliding. It's never going to collide if the distance from the sphere to the plane is greater than 1, and if it's less than 1, it will always be colliding. Next, we're going to check what happens if it's not 0, and to do this we take t0 to be the first time our sphere collides with the plane, and t1 to be the second time that our sphere collides with the plane. You can imagine if you have a sphere travelling through space, it will hit any given plane twice, once as it starts to intersect with it and once as it finishes intersecting with it. So this method just checks both of those times. All I'm doing here is I'm shifting over. It's quite useful to know that t0 is the smaller of the two, and you can see why we need to check if the dot product of the velocity and the normal is 0, because otherwise we'll end up with a divide by 0 error there. Now if t0 or t1 are between 0 and 1, then we know the collision will happen in our given time frame, and we can calculate our distance along the velocity vector by just multiplying it through t0. This will tell us how far along the velocity vector we've had to travel before intersecting with the plane, and this is in fact a very useful number to have. None of the other collision detection methods give you this. We can calculate the intersection point with the plane like this. So we just subtract the primary position plus the distance travelled from the normal of the collision plane, and that's the point on the plane where the sphere touches it. If the point that the sphere touches the plane is within our triangle, then we can return true. If not, then we will just continue and we're going to check our vertices and edges. So now, onto the vertices and edges. Both of them, as you saw in my video before, are quadratic equations. So we're going to want a quadratic equation solver. And if you remember back to high school, that's going to be our discriminant taken as b squared minus 4ac. If that's larger than 0, then there's at least one solution. And we can take the square root of the discriminant and plug it into our general quadratic equation solver. So that's just minus b plus or minus the square root of d over 2a. Again, high school stuff. I'll swap it around. I do want the smaller value to be checked first. So I'm just swapping r1 with r2 if r2 is smaller. And if r1 is between 0 and 1, then we can return r1. And if r2 is between 0 and 1, then we'll return r2 if r1 isn't. Otherwise we just return -1, and this is me telling myself that there is no value within the range that we want to check. So now we have that, we're going to set up our check for the vertices first. We can take our vertex as the index at a given point in our secondary shape array, and I'm going to calculate my a, b and c values for the quadratic equation like so. The a value is the square velocity, so that's the dot product with a velocity in itself. You can see why if we take the dot product of a vector in itself, that'll give us the square length of that vector. Next we take the b value, and that's going to be the dot product between the sphere velocity and the difference of the position and the vertex. And finally we'll grab the vertex distance as just the difference between the vertex and our position, and we want to square the distance there and subtract 1. Strictly speaking, we are subtracting 1 squared from that, but of course that is just 1 still. So finally we have our a, b and c values. We just plug them in to our quadratic solver, and if the answer is greater than 0, then we can return true. The sphere is going to be 1 unit from the vertex over our time frame. So then we're going to check our edges. If there's no collision with the plane or the vertices, then the edges are next. We can define an edge by 2 points, and we're just grabbing these again from our secondary shape array at the indices, just wrapping around. So this will check point 1, point 2, point 2 and point 3, and point 1 and point 3. And we define the edge as just being 0.2 minus 0.1. I'm now going to set up the A, B and C. This was again just a quadratic equation. It's not really going to be worth me explaining how we get any of these values. If you're interested, you can take a read through the paper, or in my video I do briefly cover what we're looking at, although functionally all you need to accept is that solving this quadratic equation tells us whether the sphere is ever exactly 1 unit from the infinite line that lies through the 2 points. So we construct the variables here. These are just my A, B and C values. I will just let you copy them down. It's not essential that you understand what they do, just that if we put them through our quadratic solver and we get an answer between 0 and 1, then we can be sure that the collision is going to happen. I'm going to notice in a second that I've put edge square there, but functionally all I'm doing here is I'm constructing all the important parts of the equation. So I'm sorry, that's a lot of things to write out, but once we've got them all in, they literally just plug in. So plug each of these 3 variables in, we set the maximum value we're interested in to 1, and if x1 is greater than or equal to 0, then we can be sure that the sphere collides with the infinite line. Now of course this isn't quite a collision yet, because we don't know if the point that it collides with the infinite line is between the 2 endpoints of the line itself. So to do that we just put it through this function here, and this tells us if the collision point is between the 2 points. Again, you don't need to really understand what it does, it will just return a value 0 to 1 if it has. So finally I'm going to make 2 more methods here, and these test not if an intersection will occur, but if an intersection is occurring at all points along the velocity vector. This is important because the other tests won't easily pick up an embedded point, and that can be a problem in certain situations. Now I didn't actually cover this in the video, so I'm going to go over what I'm doing as I do it. For our first test, which is with the vertices, we just test if at our starting point the distance from the vertex is less than 1, and if our ending point, our distance from the vertex, is less than 1. If both these situations are true, then the sphere is embedded in the vertex. And secondly, we're going to do our edge embedded test. This one is, as it always is with edges, a little bit more complicated than vertices, but the principles apply. We just use a point projected on the infinite line as our point that we check the distance from, rather than a single vertex. So to calculate all of this, we take our distance from our position to one of the points on the line, and the edge defined by 0.2 minus 0.1. And to do the projection, all you need to do is put in the values here. I'm going to be multiplying the edge by the dot product of the edge and our distance from a point on the line, divided by the length of the edge squared. And then I take t0 to be our starting distance from the line itself, and I create 3 points here. This is part of a standard test to see the closest point from a sphere to a line. The way we do this is we check the distance between the sphere's point on the line, the lowest point, and the highest point that define the endpoints of the line. So you can see that gives us d1, d2 and d3, and then running from the values here, we're just going to be checking if our shortest distance from the edge remains less than 1 for the entire duration of the travel. If not, then we'll return false, and we know that the sphere isn't embedded in the line. So now that we have these 2 checks, we'll just add them into our large checking method here. And to do this, we just want to, again, iterate through the 3 vertices of the triangle, and we're going to be checking if there is an embedded vertex or edge on each of the conditions. So as usual, I'm just going to be extracting 2 points. So we want to extract 1 point, the next one after it, looping around if we're on the last point in the triangle. And we're quite simply just going to call if our edge embedded test with the 2 points, or if our vertex embedded test, then these are our final 2 chances for the sphere to be intersecting with the triangle. And finally, if there is no collision that has occurred, so if we never return true with any of the triangles in our main shape, then we can return the entire method as false. The last thing we do is we go into our collision detector class and we're going to set up the call for the method. And that's what there is to it. I understand it's a very long method, it's a little bit complicated. I've done no effort to optimize it. There are a lot of things you can do to make it run far more efficiently, so you're not having to check every single triangle every single time. And that about does it for this video. Thank you so much for watching. I really hope that this video has been some help, or at the very least given you an idea of how you can start to implement your own detection in games. This is the last tutorial for the series now. I am thinking of doing perhaps a review of the methods that I've covered, showing you applications for each and maybe a few ideas for improving them. But that's all for this video. If you have any comments, questions or suggestions, do chuck them in the section down below. I really do appreciate all of them. And until next time, I'll see you very soon.